Sorry, I had the microphone muted there. Just to let you know, we've got 5 minutes to do this first problem. We're doing equilibrium problems. This one you'll do with a bit of resolving. We'll go on to some polygonal forces problems in a minute. Here's a hint of the diagram. Okay, so that's enough time if you understand the problem and know what you're doing and your algebra is good. You should have been able to finish it already. If not, don't worry. You'd have had enough time to get a good idea what you're doing with the problem. So the first thing we're going to do, we're going to resolve vertically is what I'm going to do. I'm going to resolve vertically, and I've got, of my T2 component, if we look upwards and make a right angle triangle, I've got this component acting up, which is going to be, if that is 60, then this is 60. So it'll be T2 sine 60, acting upwards. So I'm going to write T2 sine 60. And similarly over here with T1, okay, that'll be 30. I'm going to have T1 sine of 30. And they must be equal to what's acting down, which is the 18. So there we go. And we can simplify that a bit. Sine of 60 is root 3 over 2. So we're going to write root 3 over 2, lots of T2. Sine of 30 is a half. So we got T half of T1 equals 18. And if we resolve horizontally, okay, what we can see is the 18 is going to be 0. We're going to have cos 30 of T1. So we got T1 cos of 30. And that will be equal to T2 cos of 60. And T1 cos of 30 is going to be root 3 over 2 T1. And this is going to give me T2 over half of T2 even. So times that by 2, I get root 3 T1 equals T2. So if I call that equation 1 and this equation 2, and substitute, give myself a little more space. Okay, and substitute my answer here for equation 2 into equation 1. So I'm going to replace the T2 here with root 3 T1. I'm going to put that in there. So what I get is I get root 3 over 2 times by root 3 T1 plus the T1 over 2 here equals 18. Root 3 times root 3 is 3. 3 over 2, so that's 1.5 T1 plus a half T1 is 2 T1 equals 18. So T1 equals 9 newtons. Have a bit more space. Okay, and what we see there is we put that back in up here, and we can get T2 is equal to 9 root 3 newtons, because we're going to have T1's equal to 9. 9 times root 3 is 9 root 3. You could work that out if you wanted. I'm quite happy to leave that in terms of surds. Right, our next question here. A particle is in equilibrium under the action of 3 horizontal forces, each making an angle of 120 degrees with the other two. Prove that the 3 forces all have equal magnitudes. Now I'm going to give you 3 minutes to have a go at this question. There is a diagrammatical way you can do it, which will be very quick, or you can do it by resolving as well. It's your choice. Okay, so that's 3 minutes. You should have been able to have a go at proving that. Now, if you look at the diagram, I've drawn each of the forces and I've called their magnitude x, and we've got 120 degrees between each one. And what you realize is that you can actually draw, you can draw a triangle with these forces. And what you'll realize is if you draw a triangle, each of these forces, you know that each length is equal to x, and you'll know that the internal angle is equal to 60. And basically, because they form an equilateral triangle with each side equal to x and each angle equal to 60, that actually they come back to the beginning. So therefore, the equilibrium, they will be in equilibrium. Okay, so they must all have equal magnitudes if this is to be the case, because they each got angle 60. So therefore, each side must be the same length. But another way we could do this is we can show this that you can resolve vertically, and you can see actually if we've got x1, call these x1, x2, x3. We can show that if we resolve horizontally, we can show that naught is going to be equal to x2, and it's going to be sine of 60, and plus minus x3 sine of 60, and they will equal 0, because x2, if we make that the positive direction, this is the negative direction, then these are going to be equal, and therefore x2 must equal x3. Okay, in that. It's not horizontal, so I haven't got an x1 here. So I was just going to ask, wouldn't x1 not be horizontal? No, I haven't got x1 because I've got naught there. No, no, right, okay, you're confusing this with being up and down. This, you can imagine you're looking from above. Okay, imagine you're looking from above, and these are all horizontal forces. Basically, they're all in the same plane, these forces. And if we resolve vertically, okay, what you can realize is you've got x1 minus x2 cos 60 minus x3 cos of 60 equals the 0, because we're in equilibrium. Therefore, we've got x1 cos of 60 is a half, so we've got minus x2 over a half minus x3 over half equals naught. And we know that x2 equals x3, so we've got x1 is effectively equal to just x2, as x2 equals x3, which we showed up here. And you can show it that way as well. So you can do it either the x1, x2, x3 must all be the same, because you've got a triangle where all the angles are 60s, therefore these must all be the same length. Or we can either resolve it and show it, because you know horizontally x2 must equal x3, and then vertically, well, actually don't even, to be more specific, what I should have said actually is resolve parallel to x1. And then it wouldn't matter what direction these point in. So if I said resolve parallel to x1, it wouldn't matter what direction these point in. And this one could be perpendicular to x1 here. Okay, resolving perpendicular to x1. And then that would be a more general proof, and it wouldn't matter what way we're pointing in if we're saying that's what we're doing in our resolve. And that would be a much better proof of this, if I'm actually honest. Right, next question, question 3. This is another 5-minute question, I think. Let me just check. I've done this answer already. I think it will probably take 5 minutes. So I'm going to give you 5 minutes to have a go at this one. Okay, so that is your 5 minutes up there. So let's have a look at this question. Now, it does say using the triangular forces. Now, I'm not a big fan of using the triangular forces for this question. I'm much happier resolving parallel and perpendicular to the plane. But just for the sake of this question, we'll do it using triangular forces. So I'm going to put the 120.7 newtons going that way. I'll put the normal reaction going that way. And then I'm going to have my this one going straight down, the 36G here. And therefore, I'm going to make this angle here. I'm going to just call, well, that's my angle theta there. I'm actually going to, that's angle acting theta there. So that's my theta here. I'm going to work on it using this. So what we can see is if we use this, that we know that's a right angle, so we can use a bit of trigonometry to show that opposite over adjacent. I've got sine of theta equal to 120.7 over 36g. And if I work that out, opposite over adjacent, if I work that out, I'll get theta to be equal to 20 degrees. And so my angle here is equal to 20 degrees. So therefore my angle here is equal to 20 degrees. Next, by Pythagoras, okay, we can do the coefficient of friction. We can find out what the normal reaction is, because we're going to need to know the normal reaction because we know that F equals mu r. So we're going to work out the normal reaction. So we know that r squared will equal 36g all squared minus 120.7 all squared. And if we work that out, we get something like this. So just over 109,000. And therefore, R will equal about 331.51. So the friction equals mu R. So therefore, mu will equal 120.7 over the 331.51, and we get 0.364. Right, next question. Okay, give you another 5 minutes to do this one. Now, this one is, I think, much better done as a triangular forces than it is done by resolving. Okay, is my hint here. So this one I do think is done well with triangular forces, and it's much easier with triangular forces than it is resolving. You can do it by resolving, but I would advise using a triangular forces to have a go at this question. For those of you who are struggling to do the triangular forces, I'm going to put it in the screenshot for you in a second. I'll just ask what this angle is here. I just called that alpha and that theta. That's what I've done. Alpha and theta is just names I've given it to them. Right, I'm going to stop there because it's a case of if you see it, it's going to be quite straightforward. And if you don't see it, it's not so straightforward, judging by my class here. So what I'm going to do is I'm going to find alpha first. And what you realize, you've got three sides of a triangle. So we're going to use the cosine rule. And we know that cos alpha will equal 17 squared plus 30 squared minus 21 squared all over 2 times 17 times 30. And I'm just thinking, actually, you might want to know how I drew this triangle. So basically, I've drawn my 17, 21, and 30. If they're acting in equilibrium, then the 17 and 21 must be on the obviously away from the 30. And I just chosen an angle here to give me this angle between the 17 and the 30, the acute angle. And then I've chosen this angle here to be the acute angle between the 21 and the 30. Okay, so I'm finding the acute angles between these two. And then I can then realize I'm going to draw the 30 that way, take the 17, put it on the end of that one, take the 21, put it on the end of that one. And that's the way they've got to go. So, carrying on from here, if we do this, we get this is equal to about 0. I think I can't read my own writing. 0.73 something. I'm not sure what the next number is because I've scrawled it away. And that when you come out to do this, you get alpha equal to 42.83 degrees. Now, what you realize, alpha doesn't actually give you the angle between the 30 and the 21, the 17 newtons. It's this angle here. And we've got to take it away from 180. So therefore, the angle with the 17 newtons is going to be equal to 137 degrees. And then we go on to the cos theta, is exactly the same idea. And that gives us 30 squared plus 21 squared minus 17 squared all over 2 times 30 times 21. Now, you may or may not know the rearrangement of the cosine rule. You can just write out the cosine rule in full and rearrange it to get this. And when you've done all of that, you get theta is equal to 34.3.4. And once again, theta does not give me the angle between the 30 and the 21. Okay, you can see I need to take it away from 180 to get the angle. So therefore, the angle with the 21 newtons is going to be equal to 147 degrees to the nearest degree. So that will do for today. I think that's taken us to 35 minutes. Always try and keep these between 30 and 40 minutes long, so your concentration is optimized. Anyway, there's only one more question to do on the sheet. If you want to have a go at this one, I would advocate doing it pretty much in the same way as you do this one. There's one way of doing it. Or you could try doing it the same way as I did this question. It's just going to have different unknowns in it. You can do it the same way as I did question 1. Okay? So anyway, next revision lesson we'll be doing will be next week, probably Monday, around about 4 o'clock. We'll move on to other topics other than just resolving forces.